Hey there, day 2 of exponential growth and decay. Here we go. So first we're going to just build into the formula. We talked about this formula yesterday. A sub 0 is like your initial amount, and then you do 1 plus or minus the rate as a decimal, right? So they're going to give it to you as a percentage, like 6%. You turn it into 0.06. You either add it if it's growth or subtract it if it's decay. And then t is time, so that's going to be your exponent, and it's usually in years. So let's say like 4 years, so you would put a 4 there. All right, but first let's just get the basics going here. So if you look at the 2 examples, again, this is something we went over yesterday, a 7% increase. 100% plus 7% would be 107%. As a decimal, that would be 1.07. So to me personally, I prefer to add or subtract the percentage first and then turn it into a decimal. But you could go with the way the formula has it, which is 1 plus or minus the rate as a decimal. So 1 is 100% as a decimal. So if you look in the right column, it says 1 plus 0.07, 1.07. So 2 different ways you can get to the same thing. A 12% decrease is obviously subtraction. So we're going to be doing 100% minus 12%, which is 88%. So it retains 88% of its value each year. Now, as a decimal, that would be 0.88, which we'll find over here. 1 minus 0.12, which is the 12%, would give you 0.88. So in the formula, we need it in decimal form. So again, if you want to convert the percentages into decimals right away, like in this column, great. If you want to subtract the percentages or add them first and then turn it into a decimal, great. Doesn't matter. So here we have a 50% increase. So 100% plus 50% would equal 150%. And in decimal form, that would be 1.5. So here we'll do it in decimal form. 1 plus 50% is 0.5, which will give you 1.5. All right, 17% increase. 100%. I didn't write my percentages on the red one. Sorry. Plus 17% would be 117%. And in decimal form, that would be 1 plus 0.17, which is 1.17, 1.17. Last one, 71% decrease. 100% minus 71% would give us 29%. It retains 29% of its value each year. In decimal form, that would be 1 minus 0.71, which is 0.29. Let's get into the formula. Look at us modeling exponential growth. I hope you were singing along at home. All right, that'll do. In 2000, the cost of tuition at a state university was $4,300. Wow, that was cheap. It has gone up exponentially since then. During the next 8 years, the tuition rose 4% each year. Write a function to model the population over time. Population, I think they're talking about the cost, the tuition. So the initial tuition was $4,300. Remember, we do 1 plus or minus the growth or decay. So it's growing 4%. So 100% plus the 4% would be 104%. But we need that in decimal form, which is 1.04. And it's to the t power. T is time in years here. Does this represent exponential growth or decay? Well, obviously it's going up 4% each year, so that would be growth. What was the cost of tuition in the year 2006? Oh, great question. Great question, textbook. Thank you for your question. I would be happy to answer that question. What's going to be the exponent here? Well, it started in the year 2000. Now we're doing the year 2006. That's 6 years later, so that would be our exponent. Now remember, Order of operations, you do exponents before you do multiplication. So we're going to do 1.04. Oh, great. Somebody stabbed my calculator. Oh, that's so sweet. Thank you, guys. I'm so glad that I just offer them freely for you to use to stab them. All right, 1.04 to the sixth is 1.265319, blah, 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 blah. Just go straight into times 4,300, and we get 5,440. That's the dollars, and then we have 87 cents. There's a 1 after the 7, so we'll round it off at 87 cents. It's not too bad, right? Great. If you had to do that without a calculator, that'd be pretty tough. The city of Sterlenberg had an initial population of 15,500 people. Oh, it's been dropping by 3% each year. So it's dropping 3%, which obviously, for question B, would show a decay. So if it's starting off 100%, you're losing 3% each year, you're keeping 97% of the residents each year. So the way we're going to write that, our initial amount, 15,500. We did the 1 minus 0.03, or 100 minus 3, to get 97%. In decimal form, it's 0.97 to the t. Predict when the population will drop below 8,000. Okay, you can do this with a graph. That would make it easy if you tossed it on desmos.com, graph this function, see when it drops below 8,000. Besides that, maybe we can check, just kind of guess and check some things. So let's try when it's 10 years. 0.97 to the 10th. Oh goodness, this calculator. It's been stabbed too many times. Here we go. Minimal stabbing on this one. 0.97 to the 10th times. By the way, all right, so I already know this one's not going to work. Because if you look, we're looking for when it's 8,000, which is a little more than half of 15,500. So I'm trying to get a decimal that is around 0.5, maybe even 0.6. When I just did 0.97 to the 10th power, it came out to 0.73. So it's like 73% of its population. So already, that's not enough time. So let's try another time. Let's try like 15 years. .97 to the 15th power is 0.63. Okay, so let's multiply that then by 15,500. And it came out to 9,815 people. There's decimal people, but we don't count decimal people. We only count whole people. All right, so it's got to be more than 15 years. Let's try 20. 0.97 to the 20th. 0.54, okay, all right, times 15,500. 8,429-ish people. Hey, we're getting close. We gotta still drop it a little bit more. Let's try like 22. 0.97 to the 22nd power is 0.51 times 15,500. Oh, I did divide it by, whoops, 0.97 to the 22nd power times 15,500. 7,930. 31. All right, so it's below 8,000. I'm just going to double check because I skipped a year. So let me check to see if it happens during the year 21. Just to be sure, 0.97 to the 21st power times 15,500. So it's still over 8,000. So it's 8,176 people. So 22 years is what it takes for the population of Sterlingberg. Oh, damn. Now we're doing compound interest problems, which is very similar. You'll notice the only difference, let me see if I can make myself smaller. So the only difference in the formula is it still has your initial amount out there, which they call the principal, which is like the amount of money you put into this account. So we're talking about bank accounts here. You're still going to have 1 plus or minus, but these are all plus. The rate as a decimal divided by n. Now, n is going to be the number of times your money is compounded. So they'll say 2% compounded quarterly, which means they adjust your interest 4 times a year. So then whatever number you have down there will also come up here, and you multiply it by the time in years. So it's basically saying like how many times is your money compounded. So if it was 10 years, but your money gets compounded twice a year, 2 times 10 would be 20. So it's going to be adjusted 20 different times during those 10 years. So Clara invests $5,000 in an account that pays 6.25% interest once a year. So this is called simple interest. It's not compound interest. So it's 1 time a year. So in our case, n will be 1, which we don't need to write it, but we will for this first one. Write a function to model the population over time. Population, I'm pretty sure they're meaning the amount of money here. So we'd say 5,000, our initial amount, times 1 plus, now 6.25 in decimal form would be 0.0625 over the number of times it's compounded per year, and it's at once because it's simple interest. And then that same number gets multiplied up here by the time. So we're going to clean this formula up a little bit. 0.0625 divided by 1 is 0.0625. Plus 1 would be 1.0625. The exponent is 1 times t, which is just t, and we're going to multiply that by 5,000. So we just cleaned it up a little bit. Now, does this show growth or decay? Well, obviously, the number with the exponent is larger than 1, so that's exponential growth. How much money will she have in 6 years? So we're going to put in 6 for our exponent. 5,000 times 1.0625 to the 6th power. 1.0625 to the 6th. 1.4387 blah 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 times $5,000. $7,193.56 if we rounded. Honestly, the bank would probably give you that at 55 cents and keep the fraction of the penny. They're just like that. Thanks a lot, big banking. All right, that's awesome. So if I had a question that said, well, how much interest did Clara make? You could do the 7,193.56 minus the $5,000. She got over $2,000 just in simple interest. That's awesome. After how many years will her investment be worth $10,000? So right now it's worth $7,000. So it's going to need to be more than 6 years, obviously. Let's try 15 years. That might go over the top. 1.0625 to the 15th power. 1.0625, 15th, 2 point something. Okay, so automatically that's going to be over 10,000 because 2 times 5,000 is over 10,000. So that would be like 15,000. So that was a bit much. Let's dial it back and check 10. 1.0625 to the 10th. It's 1.8. We're going to need this to be about 2, because 5,000 times 2 would give us 10,000. So again, this is 1.8. It's not enough. So let's bump it a little more. Let's try 13 years. 1.0625 to the 13th. 2.1. Okay, that'll work. Let me try 12. 1.0625 to the 12th. We're still at 2. All right, so 12 works. And then we'll try 11. 1.0625 to the 11th. 1.9. Ooh, it's close. So year 12 will be when she is over that 10,000. So we can get that exact number. They didn't ask for that, but we're just cool like that. 12 times 5,000 is $10,349.45. Cool. Good for her. Way to go, Clara. Let's see if they gave us an initial year. Nope, they didn't give us a year, so we don't know what year it would be. A sophomore wants to buy a new car since she just got her driver's license. She found a bank that will compound her interest monthly. How many months are there in a year? 12. So our N will be 12. It pays 1.25% per month. Okay, so they kind of gave us that amount. Interesting. Usually they give you the annual amount, and then you have to divide it by 12, but they kind of saved us a step here. The car only costs 35 grand only, and she pays $750 to put in her new account. How much money will she have after 1 year? Okay, she's putting in $750. Now her money is increasing 1.25% per month. So that would be 1 plus, and again, we don't have to divide it by 12 on this one because they already did that for us. That was sweet of them. So it'll just be 1 plus the 1.25%, so 1.0125. Now remember, we have to do number of months n times number of years. So they said after 1 year, so it would be 12 times 1, which is 12. 1.0125. So the 12th power, 1.16075 times 750. All right. This sophomore has $870.57. Cool. Good for you. How much will she have after 5 years? So the only thing that's changing here is the exponent. 1.0125. It's going to be 12 times 5, which is 60. Right? Because it's 12 months each year times 5 years. 1.0125 to the 60th power is 2.107, blah, 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 times 750. 1,500, 1,580 and 39 cents. How much will she have after 75 years? The car will be in the junkyard by this time. That's probably true. 75 years. Let's see if she can even afford the car. Oh, I hope so. 750 times 1.0125. Now here we have to do 12 times 75. 12 times 75. 900. Wow. Imagine doing that without a calculator. 1.0125 to the 900th power. That's a large number. Times $750. Hey, good job, sophomore. That was a wise investment. A nice 75-year investment. We have 53776 Let's throw in our commas. Okay, nice. Just made a cool 53 million. Offer initial $750 investment. That's great. In 75 years, I don't know what that'll feel like with inflation. That's it for the notes. We done did it.